I'm going to talk about massively parallel algorithms on trees and sparse graphs. I'm Ce Jing, and this is joint work with Mohsen Ghaffari and Christoph Grunau. First, let me introduce the model that we are working with, which is the MPC model. In this model, we're given an input graph G with m vertices and m edges, and we want to solve some problem on this graph. However, the graph is too large and it cannot fit into the memory of a single machine. So we have to use multiple machines to store the input and do the computation. Let's say that we have m machines and each of them has memory size s. We assume that the total memory of these machines is just enough to store the input. So s times m is roughly equal to m plus m, which is the size of the input graph. At the beginning, the input graph is arbitrarily partitioned into m subgraphs of roughly the same size, and they are distributed among these m machines. Then the computation proceeds in synchronous rounds. In each round, each machine is going to perform some computation on the data stored on its local memory, and after that, the machines will communicate with each other, and then they'll do the next round of computation and so on. And we allow every pair of machines to send messages to each other. The only restriction here is that the total message size cannot exceed the memory limit. So in each round, the total data sent from a machine is at most s, and the total data received by a machine is also at most s. And the goal is to optimize the round complexity. The MPC model has been studied intensively, and it's known that it can support many useful primitives in only constant rounds, such as sorting, prefix sum, and array queries. Okay, so now let's look at some previous MPC results on two important problems, maximal matching and maximal independent set. There are three memory regimes being studied. The first one is the strongly superlinear regime, where the local memory is n to the 1 plus delta for some positive constant delta, where n is the number of vertices. And we also have the near linear memory regime and the strongly sublinear regime, where the local memory is n to the delta for some small constant delta. In the strongly superlinear regime, we can solve these two problems in constant rounds. And in the near-linear regime, the best known algorithms run in order log n rounds. And in this paper, we'll work in the strongly sublinear regime, which is the most challenging. Currently, the best algorithm needs square root of log n rounds to compute maximal matching or MIS. And recently, there is a conditional lower bound result in this regime by Ghaffari, Kuhn, and Whittle. It says that if we believe the hardness of the connectivity problem, then there is a log n round lower bound for maximal matching and MIS, which applies to every component stable MPC algorithm. We can see that there is still a large gap between the upper bound and the conditional lower bound. Recently, there have been some faster algorithms for some special type of graphs. The first result was a log n cubed algorithm that solves MIS on trees. And later there's a better result, a log n squared algorithm for MIS and maximal matching on a more general class of graphs, the bounded arboristic graphs. The arboristic of graph G is the minimum number of forests that the edges of G can be partitioned into. And it's also roughly equal to the average degree of the densest subgraph of G. So if alpha G is small, then the graph G is sparse everywhere. We remark that the low arboristic graphs include a lot of natural graph classes such as trees, planar graphs, low degree graphs, or graphs with bounded tree width. Okay, so in this work, we improve the previous results and obtain a log-log-n round algorithm for MIS and maximal matching on bounded arboristic graphs. We remark that this algorithm matches the conditional lower bound for maximal matching, which even holds for trees. Now I'll briefly talk about our second result on the vertex coloring problem. Currently, the best delta+1 coloring algorithm in sublinear MPC uses log-log-log-n rounds. And the question here is, can we use fewer colors for sparse graphs? For example, we know that a graph with arboricity alpha has a 2 alpha coloring. So for constant alpha, we only need to use constant number of colors. In general, this task is more difficult than the delta+1 coloring because delta could be much bigger than alpha. And this problem is also harder than the MIS or maximal matching, since if we can color a graph using constant number of colors, then we can iterate over the colors and get an MIS by the simple greedy algorithm. And we also know that there are several log-n round local algorithms that can achieve this. So the open question is whether we can solve this in sublinear MPC using poly-log-log-n rounds. In this work, we did not solve this question, but we give a very efficient algorithm that solves a special case. We can color a tree using 4 colors in order log-log-n MPC rounds, using only order n words of global memory without any log factors. For the rest of the talk, I'll focus on our first result, which is a log-log-n round algorithm for MIS and maximal matching. Let's first review the algorithm from previous work by Behnezhad and others. Their first step is a degree reduction procedure. They can find a matching or an independent set of the input graph such that after removing the matched edges or removing the vertices adjacent to the independent set, the remaining graph has very low maximum degree, which is only poly alpha log n. This step takes log-log-n squared MPC rounds. Then they apply the algorithm for general graphs by Ghaffari and Wito with running time square root of log delta to solve the remaining graph. And they finally combine the solutions. So if alpha is small, then this step is very efficient, and the bottleneck is the first step. Our contribution is to implement the first step using only log-log-n MPC rounds. Now let's look at the first step, the degree reduction. It uses a local algorithm by Barenboim and others as a black box. In this local algorithm, the messages and state descriptions have length polylog-n bits, so we can simulate in MPC with small memory. And this algorithm achieves the following. Assuming currently the maximum degree delta is much bigger than poly alpha, then let H be the set of high degree vertices in the input graph. By high degree, we mean it's bigger than square root of the maximum degree. Then the algorithm uses constant number of local rounds to find a matching or an independent set in the graph, such that in the remaining graph, the number of high degree vertices decreases by a factor of delta. So a high degree vertex may get removed or matched, or maybe many of its neighbors get removed, so it becomes a low degree vertex. Okay, so if we repeatedly execute this black box, say we run log base delta of n many times, then in the end, number of high degree vertices becomes 0, which means the maximum degree already drops to square root of delta. This procedure is called a phase. So in one phase, we reduce the maximum degree by a root delta factor. So after log delta phases, we can reduce the maximum degree to very small, so the whole degree reduction step is finished. Now let's look at how to simulate this local algorithm in MPC. We'll do a round compression using the standard graph exponentiation technique. If the d-hop neighborhood of vertex V can be stored into one machine, then we can simulate d local rounds for this vertex V in constant MPC rounds. The d-hop neighborhood can be collected in log d MPC rounds by doubling the radius in each round. Now recall that phase 1 has a log base delta of n local rounds. Let's set the radius d to be small enough so that the neighborhood size delta to the d is smaller than the local memory limit. Then we can simulate phase 1 in constant number of rounds. And this reduces the maximum degree to root delta. Since the maximum degree becomes smaller, we can collect the neighborhoods with a larger radius without violating the local memory restriction. So we can double the radius in constant number of rounds and then simulate the next phase also in constant number of rounds and so on. So every phase has constant number of MPC rounds except for the first one, which needs log n rounds to collect the initial neighborhood. There are log delta phases in total, so the total round complexity is log n. However, in this algorithm, every vertex uses n to the delta local memory, which means that the global memory is n to the 1 plus delta. This is superlinear, which is usually not allowed in the definition of MPC. So we have to reduce the global memory to be near linear. Here is the solution from the previous results. Since in the degree reduction procedure, our goal is to remove the high degree vertices. So we only need to simulate these high degree vertices. Other vertices are irrelevant since they already have low degree. So we don't need to simulate them in this phase. This observation can reduce the global memory because now we only need to store the neighborhoods of H, which is the high degree vertices. And we know that the size of H is decreasing very fast. So the idea is that as the size of H decreases, we gradually increase the radius d and maintain the global memory to be near linear. So after I MPC rounds, we finish 2 to the I executions of the local black box, and the radius becomes 2 to the I, which is roughly equal to the number of finished local rounds. In constant number of MPC rounds, we can double the number of finished local rounds and also double the radius. This phase is finished after log n MPC rounds. However, the downside of this algorithm is that in the next phase, the high degree threshold will drop, which means some new vertices will become relevant. But they were not relevant in previous phases, so we didn't store their neighborhoods. So in this phase, we have to collect their neighborhoods from scratch, which takes log n rounds. We have to do this for each of these log delta phases, so the total round complexity becomes log n times log delta. Now we'll describe our improvement. Notice that after we finish part of the simulation in phase 1, there are already a large fraction of vertices that have become irrelevant. So we don't need to wait for phase 1 to finish completely. We can just try to start the next phase's computation earlier on these vertices. So our algorithm is essentially a pipeline version of the previous algorithm. We'll pick a parameter t, and after the start of phase 1, we wait for t MPC rounds and then start phase 2 and so on. So the total round complexity is log m plus t times log delta. And we can see that the previous two algorithms roughly correspond to t equal to 0 and t equal to log n. Our plan is to set t to be some big enough constant so that we can somehow reduce the global memory to near linear and at the same time achieve log n round complexity. Okay, now we take a closer look at the pipeline algorithm. Within each phase, the algorithm was similar as before. We maintain that the number of finished local rounds is roughly equal to the radius of the neighborhoods that we collected. And we can double them after each MPC round. So for example, at time capital T, the phase 3 has already finished 2 to the capital T minus 2t executions of the local black box, and the radius is also 2 to the capital T minus 2t. The most technical part is to control the global memory. In the ideal scenario where there was no pipelining, we've already seen how to do that. In the ith phase, the max degree is at most delta I minus 1, which is delta to the 1 over 2 to the I minus 1. And the number of relevant vertices is already reduced by a factor of delta I minus 1 to the ki, where ki is the number of finished executions. The size of each di hop neighborhood can be controlled using the maximum degree. We multiply them and get the global memory bound. That is the ideal scenario. However, in our case, we pipeline the phases, so there may be some pending vertices which have not finished their simulation in previous phases. And if our neighborhood includes these vertices, then we cannot control the neighborhood size because their degrees could be much larger than delta I minus 1. So this will affect our memory bound. One solution might be to ignore these pending vertices with very high degree, so the neighborhood size can still be controlled. But then we would have the same problem as before. we will have to collect the neighborhoods from scratch again after these ignored vertices become relevant. So our actual solution is simple. We simply continue to collect and grow their neighborhoods as usual. And we'll see that by a more careful analysis, we can still bound the memory. But for the simulation, the only thing we can do is to wait for these pending vertices to finish. We will temporarily mark the states as pending, and if a pending vertex communicates with some other one, it will also become pending, and so on. As soon as they finish previous phases, we will know its actual state at the beginning of this phase, and then we can resume the simulation around this neighborhood. Okay, so now we'll describe how to bound the memory. Suppose we are simulating phase I. For a pending vertex V, there are two possibilities. First, V itself may still be active in some previous phase J. So V belongs to Hj, which is the set of high degree vertices in phase J with a degree between delta J and delta J minus 1. The second possibility is that V is close to some other vertex that is active in a previous phase. And the pending state propagates to V after we simulated some local computation. Let's say we simulated Ki executions of the local black box in phase I. Then this means V is at most order Ki distance away from an active vertex in previous phase J. Now let U be the highest degree vertex that is within this Ki distance from V. And let's suppose U is in Hj. Then V is reachable from U by an Ki step path, and every vertex on this path has degree at most delta J minus 1. So the number of such vertices is at most the size of Hj times delta J minus 1 to the power of Ki. Using this inequality, we can bound the total number of high degree vertices in the current phase I. The number of non-pending vertices, which is the first term, can be easily bounded because they should satisfy the property of the local black box algorithm. And for the pending vertices, we simply sum up over all previous phases J. And we can also similarly bound the total size of the collected neighborhoods. Okay, so now we have this inequality, and we introduce another tunable constant C, which is the ratio between Ki and Di. Then, by picking some big enough values for constant C and T, which is the lag parameter, we can use a simple induction to show that the global memory is smaller than n. The induction works as follows. We plug in the induction hypothesis for every j smaller than I into this summation, and notice that the exponent on the denominator is some constant times dj minus some constant times ki, and we can make it a big enough positive number by picking a big enough value for t, so that the summation is dominated by geometric series and we can get the desired upper bound. And we can also bound the local memory. Suppose the highest degree vertex in the neighborhood of V comes from Hj, then we use the upper bound that we have shown. Combined with that Hj is at least 1, then we can get an upper bound on the local memory by setting C to be big enough. So to conclude, our key idea is to use pipelining to reduce the round complexity while keeping near linear global memory. And we have some open questions. The first question, does our technique have other applications? And the second question, which we already mentioned, is there a polylog n round MPC algorithm that can color constant aberracy graphs using constant number of colors? Thank you.